Should we start? Yeah. All right. Welcome, everyone. This is the famous after lunch session, just so you know. But no, luckily for you, this is going to be a really, relaxed and easygoing session. So you can take it easy. Actually, no. Not at all. This is actually kind of technical session with lots of information. And, after all, it's about Git. So I hope you guys have had your coffee and you have it ready to go. So let's get started. My name is Enrico Campidoglio. I work as a freelance programmer. This is me freelancing from home. So I'm a programmer, but I also do a lot of training. But the training I don't do from home. I actually travel to the places. We are not here to talk about that, though, nor the fact that I once had hair. We are here to talk about Git. So how many of you are using Git today? OK, so all of you. That's good. Do you think that Git is hard? No? How many of you think that Git is hard? OK, kind of half. So I guess the other half think that it's easy or medium. Well, I, for one, once thought that Git was hard. Well, complicated. And I was wondering why. So I don't know if you ever Googled for why Git is hard, but I did. And you get a bunch of different kinds of results where people complain and they say, I hate Git. Git is complicated. Various degrees of frustration. But at some point, you see, Git is a nightmare. But then, why is Git good? So, someone is thinking about the fact that Git might be good. So I became curious, and I thought to myself, let's investigate this. So the question went from being, why is Git hard, to what is Git? And so began my journey to understand what Git is. So this session is what I've learned during this journey of really understanding what Git is and what came after it. When you come out the other side of this journey, hopefully you will have a different relationship to Git. So, the first thing you do when you research something, you find the XKCD comic for it, and this is the one for Git. So, this is Git, and it's a tool to collaborate through a beautiful distributed graph theory tree model. OK, so how do you use it? No idea. You just memorize these commands, and if everything goes bad, you delete everything and start over. Yeah, not really the answer I was looking for. However, if you look at this, there are some kernels of truth here. So, beautiful distributed graph theory tree model. Is it just a joke, or is there something real there? So next step was, of course, Wikipedia. And my question was, what is a tree? And I was like, not really that. But eventually I found, that's another tree I was looking for. This is the tree I'm looking for. And the tree, what is a tree then? A tree is an undirected graph of nodes that are interconnected by exactly one path. OK. We have something, we have a base, conceptual base to start from. OK. Now, have you ever run the command git log? I guess you've done it in some way or another. What comes out of git log looks a lot like this, where every one of those boxes is a commit. Those commits, they are connected. And at the end of one of these lines, the latest commit in a line has a branch name. Do you recognize this? Yeah. Now, of course, you can have different branches. Now, let's look at this. And can we say that this is a graph? Yeah, we can say that this is a graph. It's a bunch of nodes with interconnected. So that's a graph. But let's look at how many ways there are to go from one node to the other. So from that node to this, how many paths are there? One, yeah. What about from this to this? How many ways are there to go from one to the other? Still one. So, yes, this is a graph where every node is interconnected by exactly one path, right? Just like the XKCD comic said. So yeah, this is indeed a tree. But now let's take a look at these nodes. The definition of tree was that it was an undirected graph, which means you can go either way. But in Git, we know that every commit just knows about its parent. A commit doesn't know how many commits come after it. They just know what the parent is. So this is not an undirected tree. This is a directed tree. Now, let's consider something else. What if you merge those two branches? Now, this is the plot twist. Now, remember my question before. How many paths are there between nodes? Let's try it again. Let's go from here to here. How many ways are there? Two. Yeah, no longer one. So this is officially no longer a tree. And that's why the XKCD comic said that it was a graph. In the graph theory, it was a tree model. It was not really a tree. So this is a directed graph. Now, let's take a look at these nodes. You can see that there are no circular references. You cannot go back. There is exactly one way. You can't go either direction. So this is a directed graph. Not only that, but it is also a directed acyclic graph because it doesn't have any recursive reference. And this is exactly the object model that is the foundation of Git. Git is a directed acyclic graph where every node is a commit in your history. And of course, if you look around in the internet, you usually find this shortened to DAG, or to better remember it, you can say DAG. Now, let's look at this again, and let's unpack one of those nodes, which is a commit, right? So let's look at the object model inside one of those commits. So you have a commit. Now, what's inside a commit? I'll tell you. Inside a commit is something called a tree, again. But the tree is just Git's way of representing a directory. And inside a directory, there are files, and those files are called blobs. Now, as you said before, a commit has a reference to its parent, which has the exact same kind of graph underneath. And at the end, of course, you have the branch reference. Now, this is basically everything there is to Git. Git is a graph, a directed acyclic graph, where every node consists of trees and blobs. So you see that it's actually pretty simple. Of course, those objects, you recognize them probably as those values. Have you seen those values when you use Git, either through a GUI or through a command line? Have you wondered what those are, those long strings? Those strings are the result of when you run a hash algorithm on those objects. More precisely, the SHA-1 hash algorithm. Or if you are into the, in the Git community, we say the SHA. You don't say SHA-1. So the SHAs are the IDs, the unique IDs for each one of those objects. So a commit has a SHA, and a tree has one, and a blob has one. So we said that this hash is calculated by running the hash algorithm on the object contents. So that's easy to say, because if you run it on a file, of course, you're going to get a hash of the file's contents. So that's easy. What about a tree, a directory? How do you run a hash algorithm on a directory? Well, you run it on the directory's path. What about a commit, which is an object of in of itself? What does a commit contain that you can possibly run a hash algorithm on? So that is what we're going to find out. We're going to take a look behind the scenes, and because I see some faces where they're skeptical, they say, I don't believe you. This is not how Git is. It's too simple, ridiculously simple. So what we're going to do together is we are going to create a commit, but not like the way you usually do it. We are going to create a commit by constructing this graph from the blob to the tree, to the commit, to the branch, from the bottom up. And in order to do that, I'm going to use some commands that you have probably never heard of, and that you, after today, will probably never see again. Because those commands are the low-level commands. Those are called plumbing commands. That if you have a Git installation, you have those commands. But those are, they directly manipulate that graph. So you normally don't use them because other commands have been built on top of them to be more user-friendly. Can you believe it? The high-level commands are there to be user-friendly. So imagine how these are. But these are the basic commands that were there from the start. When Linus Torvalds developed Git, he didn't write the commands that you use every day. He wrote these ones, and then he left it because he was happy with it. And then the Red community took over the project and built, let's make Git more user-friendly. Yeah. All right, so what we have here is a command prompt that's pointing to a directory which you see here. And this is our sample project. It's a directory called src, and it contains a calculator. Let's look at that calculator. It's an embarrassing C program. It's not even a calculator. It just tells you that it is. But it doesn't really matter. This is what we're going to commit using the plumbing commands. And as a reference, I put the graph that you saw before. We'll keep it as a reference, in the bottom part of the screen. Okay? Now, this is not even a Git repository at all. So let's start by running the famous git init command, which transforms this regular directory into a Git repository. Now, let's watch what happens on the right. A new directory appears called .git. Do you know about the .git directory? Have you ever looked inside? Yeah. All right. If you have, then you probably know what's there. If you don't, I'll show you. Here is a directory called objects. Now, we have been talking about an object model. So it stands to reason that all those trees and blobs and commits, they're going to be stored there. And right now, there are just 2 directories, and those are empty. What about the branches? We usually hear that the branch is just a reference to a commit. Well, there is a directory called refs, so that's probably where they go. Refs, heads, empty, empty. Everything is empty here. And indeed, if you run git log, it's going to tell you don't have any commits yet. Okay? So let's start by committing this calculator file. Now, I also told you that everything is hashed, right? So the first thing you do if you want to commit a file, you need to ask Git, hey Git, run your SHA-1 hash algorithm on this file so that we can get an ID back. And the command is called hash object. And of course, then you give it the path to the file. And Git gives you this famous SHA back. But did you notice that nothing happened here? That's because Git is being developed by programmers. And of course, if you just ask it for a hash, it will give you exactly that. It won't actually store the file anywhere. If you also want to store it, then of course you need to say hash object -w, which stands for write. And now we have a new directory called B5, which you recognize are the 2 first letters in the hash. Now, what's inside this directory? It's a file that is named after the rest of the SHA. Now, stands to reason that we should be able to look at the contents of that file, right? It should be our file. Do we agree on that? So if we just try to read the contents of that file, what do we see? Garbage. So, turns out that when you ask Git to store your files, it is going to zip them because, text compresses really well. So in order to look at the contents of the file, you need to use another plumbing command, which is called cat file. Doesn't have anything to do with cats. Then you say print, and then you give it the hash, which I forgot to copy in my clipboard. So let's hash it again, because those are kind of hard to type. So cat file, P, and indeed we get back our file. So yeah, if you notice, this one is 138 bytes, and the original was 160. So yeah, indeed it's compressed. Okay, so now we have a blob. Next step is to have a tree, which represents the directory src, right? Now, would you expect that there is something called create tree, something like that? Well, there is, but you can't invoke it on a directory. Because what we've done here so far is that we have told Git, save this file in your object database. But Git is not going to keep track of it. If you make a change to the original file, Git is going to completely ignore it because we haven't told it to track the file. And how does Git know which files it should track? Well, it keeps a list of paths of all the files that it should track. And that list, for once, is called exactly what you expect. It's an index. It's an index it's a registry of files that it should keep track of. Have you heard about the index? Yeah. When you say git add, you are adding a file to the index. And you are telling Git, please Git, keep track of this file for me. So the low-level command to add something to the index is update index -- add. Now one might wonder, why isn't there a add index? I don't know. But there is an update index -- add. All right? Next thing you need to say is, okay, is this a read-write text file or is this a script? And the way you tell Git that this is a text file that you can read and write is, of course, by passing this number. This is the Unix way of expressing read-write flags on files. Next step is to pass the hash of the blob, because we're adding a blob and we're telling it to track it. So we need to tell it also the path on the working directory. New file appears called index. Let's take a look at the contents of that file. What would you expect to see? More garbage. Well, it turns out that, so imagine that in that file, there is an entry for every file in your project. Now, think about your biggest project. How many files are there? Think of that number. There's going to be a line in that file for each one of them. So, of course, one does not simply store such large lists in a text file. you store it in some kind of binary format, which is what the index is. But of course, you can look at it by using another plumbing command called ls_files. And then you say stage because you want to see all the information. And what you get back is exactly one line. You recognize this is it's our blob. This is the fact that it's a read-write text file. Here is the path. And what is this? Well, this session is only an hour. So if you want to know what that number is, you just find me afterwards. I'll be around. And I'll show you exactly what that number is. For now, you just have to wonder. So now we have added an entry to the index. Next step is, so Git has all the information it needs now to create a tree. It knows the blob, the ID of the blob, the SHA. It knows the path that it points to. So now we can, parse that path and create a tree for every directory. So now we can say git write tree. And now we get 2 more of these. And you might wonder, why 2? Isn't there just one directory? Yeah, I wonder that too. So let's print the contents of that tree. Oh, it contains another tree. Let's take a look at that tree. Cat file -p, and there you have our blob. So now you see that Git creates a tree for the root of your project, and then it creates another tree to represent the src directory, and under that tree you have your calculator blob. Okay? So you can basically see their directory structure there. Okay. So now we have one blob, 2 trees. Now we need to create a commit. So we are approaching the answer to the question, what is a commit then? So let's copy the hash of the root tree. And now let's invoke commit tree. Pass the hash of the tree, of the root directory. And now you can also pass not multiple trees, just one tree. And then you pass the message, adds the calculator, and we get back another hash, which of course is saved inside here as well. It's 141 bytes. What could possibly be in that object? Let's take a look. It's metadata. It's information about the commit. It doesn't have anything to do with the files that it contains. However, you see that a commit has a reference to the root tree. And of course, you know that from there you can recursively list the content until you reach the blobs. So that's one field. Another field is the name of the author and the email address. And then you have this number. Do you know what that is? Almost. That is what it's called, is usually called the Unix epoch. That's a timestamp. And why is it expressed as that number? Well, you can, of course, convert it to another format. So what is that number? That number is the number of seconds that have passed since January 1st, 1970. Yeah. And that's how you store a date in a Unix system. You store it as that number. Now, let me open a brief parenthesis here. So you guys are programmers, right? Now, if your task is to store this number, what data type would you choose? You have to store it in a database of wherever. Which data type would you choose for that number? Long? Yeah? Int? Yeah, well, let's take int. Int is probably the default in many programming languages. And int is, what is int actually? It's a signed 32-bit integer, right? Now, this number is the number of seconds that are passing. So this number is increasing. It's already increasing. I'll show you. And it's never going to stop increasing. So at some point, regardless of what data type you choose, you're going to reach the end of the possible numbers you can represent with that data type. Now, it turns out that if you store it as a signed 32-bit integer, you're going to run out of space at some point, and that point in the future is not that far. It's January 19, 2038. So 18 years from now. At 3 a.m., 3:14:07 a.m. on January 19, 2038, we are gonna overflow the int. And you know what happens then? Because it's a signed data type, it's gonna wrap around and go back to minus exactly the other end of the spectrum, which you can also convert into a date. And that date is December 13, 1901. So this is called the Unix 2038 problem. Now, if you think about Unix, of course, Linux is a Unix operating system. Do you have an Android phone? Yeah, that contains dates in this format. Also, if you have iOS, it's also based on Unix. Think about all the databases that exist in the world. Postgres, they all store dates in this form. MySQL. Turns out that if you have an old enough Android phone, you can try to set the date to this January 19, 2038, and Android will crash and the phone won't boot again. Yeah, so that's kind of interesting. So, but of course, I know, we found out about this problem around 2006. It was actually a chat program by AOL discovered this problem. So a transition has started, so new versions of these operating systems, they are storing it as a 64-bit, still signed integer. But that gives us more legroom. So now the limit is going to be something around year 2 billion. So it's a problem for future generations. So modern systems, they store it as 64-bit. But older systems still have this problem. But let's not worry about it now. I mean, we still have 19 years to go. So brief parenthesis there. Let's look at this again. Now you might wonder, why are there two fields, one author and one committer? Those are usually the same for most projects. But remember that Git was created to store the history of the Linux kernel. And in the Linux kernel, since it's so critical to many systems, you cannot simply submit commit code to that. Not even close, actually. You can submit your code, and then it's going to go through a review process where many people are going to have to look at it and sign off that, yes, we can integrate this code into the kernel. So in the end, you will have one person who is the author of the change, and you will have another person who is the one that signed off last and said, yes, I'm responsible for this code being integrated in the Linux kernel, and that's the committer. And you want to keep track of both those. So that's why it's two different fields. And then, of course, you have the message. So this is what a commit is, and this hash is the result of running the SHA-1 algorithm on top of all these fields. All right. So now do you think this is this interesting at all? Is it exciting? Maybe not. I'll show you something that's even more exciting. Now we're going to create a commit using the regular commands, the ones that you're using every day. So because we need two commits, So let's just, yeah, by the way, nobody told me. Let's run git log. Ooh, still don't have a commit. What did we forget to do? The branch. We still haven't created a branch. If we close this, remember that the branch are just references pointing to commits. This heads directory is still empty. Let's hope that I have the, no, I don't. Let me see. There you go. This is hopefully the right one. So, do I have it in the clipboard? Let me just copy that by using the menu. Yes. Is it? Yes, perfect. Okay, so how do you create a branch then? Well, you use another low-level command called update ref, like update index. You give it, what commit should this branch point to? This one. And first, let me say, where should it be created? It should be created into refs, heads, master, and then you give it the hash of the commit. Oh, the other way around. Git update ref, this refs, heads, master. That was not the right one, right? That was not the right. Okay, so let's take a look at. Well, you know what? I think I still have it here. Now, which one of those was it? No, I'm going to use history here. Forgot to copy. Oh, yes. There you go. So let's not lose those hashes, because otherwise I need to delete everything and start over. Update ref, refs, heads, master. Better. That was the right one. At least Git told me, hey, this is not a commit. You cannot point a branch to a tree or a blob. You need to point it to a commit. So now let's run the git log, as indeed we now have history. Okay, so now let's create a commit using the regular commands. So we have two commits. So let me first open up this calculator file just to make a change. Let's make a meaningful change. Have you written a comment like that before? I have. Just to make sure everybody's on the same page. Now let's add the, now you know what happens when you say git add, right? It's going to take the file, create the hash, save the blob, and add it to the index. All in one command, git add. And then you say git commit. That's a useful comment. And now we have two commits. Now, the latest commit we have is the one we have just created, and this is the one we created before. So now let's grab this commit ID, and let's print its contents. You see a difference compared to before? You still have a tree, but now you have another field, which is the parent. And this is the commit hash that we had before. So indeed, a commit keeps exactly one reference to its parent. Now, of course, if you have a merge commit, that's going to have more than one parent, so we'll have two lines there. Parent 1, parent 2. And I can tell you this, you're probably never going to encounter it, but a merge commit can have more than two parents. It can have n number of parents. That is called a octopus merge. I actually never done it in my life, but I know it exists. You basically have 4 branches and you merge them all together into one. Imagine the merge conflicts. Yeah, let's not do that. So now I want to take this tree and I want to take a look at it. So now, before we did bottom up, now we do top down. We start from the tree of the latest commit that we did, where we added a comment. And let's drill down. So now this is the root tree. Now we get another tree. Let's print the content of that. And now we have reached the blob. So this is the new blob, right? Now let's take a look at that. What do you expect to see? If I look at the blob of the file that I modified now, I changed one line. What do you expect to see in the blob? The diff? It's the entire file. Yes, so what happens, every time you commit, Git creates an entire snapshot of all your files in your entire working directory. All the files, all the trees. It's a snapshot of how things are the moment you commit. And that's for every commit. Now, this is powerful because if you've ever used Git's feature to rewrite history, where you move commits around, you change the order, or you squash them together, that's possible because every commit is its own snapshot, it's its own unit. So you can move them around, and it doesn't really matter. That wouldn't have been possible if Git just recorded the differences from the previous one, because it would have been impossible to reorder them, which is the main difference between Git and all the other source control systems that came before it. All of them saved just the difference. It's called the delta, while Git saves the entire snapshot, which means that if you run something like git diff and you say, show me the difference between the commit that came before master, you give it a reference, a branch, and then you say, go back one parent because you can only go backwards. So that's a syntax that means give me the parent of that reference, and of course you can go back. The parent, the parent, the parent, the parent, the parent. And if there are a lot of them, you can say, go 10 backwards. Anyway, give me the difference between the parent of master and master. It's going to show, yes, indeed, you modify that line. But what if you invert them? The diff is going to be the opposite. Those diffs are calculated on the fly, because Git has all the files every time, in every commit. But now I can see some of you going, shaking their heads and say, yeah, that's why my hard disk is full. And indeed, it's kind of wasteful. Imagine all the commits. Just think about the Linux kernel, all the files that are there, and the thousands upon thousands of commits. How much space is going to take? So those are called loose objects. And those are created when you just work with your repository. Every time you commit, it's loose objects, because those are fast to look up. But at some point, Git is going to say, it's time to tidy things up here. So it's going to run something called a garbage collection. Yes, indeed, Git has a garbage collector, where Git is going to look for those blobs, run a heuristic algorithm on those files to determine what blobs are similar, what blobs represent the same file with minor differences, and then it's going to just store the difference. Okay? So it's going to look at all the blobs, find the same file across multiple blobs, then determine what is the first version of this file, and then store the deltas. And that's a command that you never need to run directly, but it's run regularly. It's called git repack. And look what happens in here. All those objects have disappeared, and they have been packed into a so-called pack file. And pack file contains just the differences. Indeed, you can say that there is exactly one delta, because we just made one change. Okay? And then, of course, you can take a look at, you can say git, hey, how many objects do you have? Right now, I have 0 objects. Okay, but are there any in the pack? Oh, I always get those wrong. Yes, so I have 0 loose objects, but I have one pack file, And that path file contains exactly 8 objects, which are the ones that we created together, the trees, the blobs, and the commits. All right. Was that interesting? Yeah? Good. So let's take a look then. Now with all this information, let's take a look at what is Git then, given all this. Git is a snapshot machine with a domain-specific language built on top of it. And that domain-specific language are all the commands that you use to manipulate that graph. You have seen how we used commit tree and write tree. All those, you can see them as a domain-specific language to manipulate that kind of graph. So Git is actually a content tracker. It's not even a source control system. It can track anything, right? This directed acyclic graph model isn't specific to tracking source files. It can track anything. So it's a content tracker. But if you consider the fact that Git represents files as blobs and directories as trees, you can say, oh, by the way, I forgot to mention, that if it's a content tracker, it even says it in the manual. Git is a stupid content tracker. And why is it stupid? Because it's really simple. I mean, at the core, that's all there is to it. So it's a content tracker, but it's also a file system because it has abstractions for what are really files and directories. Those are called blobs and trees. So it's a virtual file system. And indeed, if you look around in the documentation, you'll see that Git is often referred to as a virtual file system. But let's not stop here. We also saw that every object in that model has a unique ID, which is the hash, the SHA. So really, Git is a hash table, just like JavaScript. Are there any JavaScript programmers? Yeah. I was hoping for none, but that's OK. So Git is a hash table. It's a key-value dictionary. JSON, let's agree that JSON is a key-value dictionary, where every ID points to one of those 3 objects. So indeed, Git is very simple at its core. But I don't know, you might wonder, why would I care about all this? Do I have any use for this information? Well, if I have this mental model of what Git really is, because Git is basically this, how does that help me on my day-to-day work? Well, let me show you a quote first. Let's all agree that having a clear history of your source code is a good thing. Can we agree on that? Because it's a record of how your code base changed. So if you keep it clear, that's going to help when you go back and look at why something has been changed to the way it is. So keep your own history readable. However, if you have ever used a source control system, you know that those source control systems that you have used in the past, they were pretty unforgiving. Once you commit something, that's it. You can't go back and tie things up afterwards. So how can you keep a history readable then? Well, the only way is not making any mistakes. Or some people do it by just working things out in their head first and never make mistakes. So that's how they have a clear history. For the rest of us, we can use stuff like git rebase, that is, go back and rewrite history after the fact to remove commits that don't make sense or squash them together or change the order so that history becomes readable. But you are still free to make mistakes. And you know who said this? Linus Torvalds. So, and he also said something else. He said, if you can summarize this in one sentence, is don't expose your crap. So you can, in a way, you can work the way you prefer, have your own workflow, commit often, commit seldom, doesn't really matter, as long as you can go back afterwards and make it readable for everyone else, including future you. So let me give you an example of what you can do. Now, this is a sandboxed environment. It's Git in a browser. But it's not really Git. It's an implementation of Git in JavaScript. So it doesn't support every command, but the good thing that it does is that it draws the graph as you work. So if I make a commit, and I give it the message B, then it's going to show me how that affects the graph. All right? So as you can see, we have a master branch. I just made a commit. You see that it looks exactly like the things we've been looking at for the past 45 minutes. But if I have this mental model as I work, let's see what I can do. Let's see that I'm in the master branch and I made a commit. And now I'm on a roll. So now I'm working and saying, oh, let me implement this feature. I'm really getting somewhere. BC, let's make D. But then a bug report comes in. Someone asks me, you need to fix a bug. OK, but now I have 3 commits that are not supposed to go anywhere yet. But I have to fix the bug, and the bug was in the snapshot represented by commit A. So what do I do now? Well, let me first create a new branch, and you know how that's created, update ref, well, the low-level command. But you say git branch, let's create a branch called experiment that points to the commit where I'm at right now. And now I have a new reference pointing to that commit, which means I can take the master reference and move it back to where it was when I started. So I say git reset hard, which means I really mean it. You really need to move this now. And you say, where do you want to move it? Well, to A, so you can use the SHA, or you can say from head, or let's say master, how many commit backwards? 1, 2, 3. So 1, 2, 3. And now master is just a reference. I just moved it to point to a different commit. Now my working directory is synchronized with that snapshot, right? And now I can fix the bug and make a new commit. Now I want to resume work on my experiment. So I synchronize my working directory with the snapshot that was in experiment. So I check out experiment. And now my files are exactly as they are in that snapshot. However, that bug fix will be really good to have where I'm at right now. So let's grab that commit or apply the difference between the snapshot in bug fix and the snapshot where I'm at right now by using a command called cherry pick, which means take that commit and apply it on top of where I'm at right now. So now that commit appears twice, because it's not like I moved it. I just took the snapshot that was there and applied it on top of mine and created a new commit. But now it looks like the bug fix came after the D, which is actually what happened. But I don't want that history. I don't want it to look that way. I want to tidy things up so that the bug fix came before my experiment. How do I do that? Well, let me just reset again. So that I remove the latest cherry-picked commit. And instead, let me rebase what does rebase mean then? This branch is based on top of A right now. What I want to do is that I want to base it on top of bugfix instead. So I change the base of that commit. So that's what rebase means. And look what happens now. So I basically took that sequence of snapshots and moved the parent that once was A, and I moved it to become the bug fix. And now it looks like the bug fix came first, and then my experiment came afterwards. Now, all these operations are possible because Git is a graph of nodes. And every node points to a snapshot. So that is why it's useful to know these things, because you can work the way you prefer. You don't have to adjust yourself to the tool. Instead, the tool adjusts to you. And at the same time, you can have a clean, beautifully clean history. Now, there is an argument going, which is a philosophical argument you might encounter on the internet, which is, what do we really want? Do we want clear history, or do we want true history? Because, of course, as you saw now, when I rebased, it looks like bug fix came before my experiment, while in reality, the bug fix came after in time. So that's not what actually happened. I tidy up history to make it look better. So if you think about it too much, there is an argument about, so history in Git is not really a reflection of what happened. It's what you want it to look like. So are you going back and changing history to make it better? How does that apply to human history? Yeah, don't think about it too much. What I can say, my point of view, is that the history in the context of source control, history is useful if you can understand it. It's not useful if it's a mess. So I prefer to tidy things up, even if it's not a reflection of what actually happened, because I know how life was when source control systems were a reflection of what actually happened. History was a mess. So it's better to have it tidied up. And that's the example I gave you before. So if you are going to remember one thing from this session, I want you to remember 3 things. This is the first one, that Git is a content tracker, and nothing more than that. It just happens to be used as a source control system. The second thing is, do not ask what you can do for Git. Instead, ask what Git can do for you. I mean, choose your workflow. And when I say your workflow, I mean your personal workflow when you're working, but also your team's workflow. How do you want to collaborate on this project? How many branches do you want to keep? What's your merge strategy? Choose that regardless of what's possible. Don't think about rebase and cherry pick and merge conflicts. Just decide what does your project need and how does your team feel comfortable with, and then choose the way you use Git to support that workflow. Because Git doesn't have an opinion. It supports everything. It's just a graph. And the third thing is to keep a clean history. 5 minutes to go. Before I leave you, I have a Pluralsight course out. I don't know if you have Pluralsight, but there are also 30 days trial called Advanced Git Tips and Tricks. I know advanced is probably not the first thing you're going to look up when you learn Git, but that course will show you techniques similar to the ones that I've shown you here. Enough with the shameless plug. Thank you for your attention.